keep going down this Gibbs free energy and spontaneity rabbit hole even further. And we can use this same relationship, delta G equals delta H minus T delta S, to not only determine if something is spontaneous, but we can determine at what temperature something is spontaneous, okay? And as it turns out, there's a very special value of delta G when something is spontaneous, or I should say right at the threshold, and that's when delta G equals 0, okay? So for example, if we consider again ice melting, and we look at this scale here, energy versus temperature. So we know ice melts at 273 Kelvin, right? Let's just remind ourselves that that's 0 degrees Celsius. And so what that means is if I have an ice cube above 0 degrees Celsius, it should be spontaneous, right? The delta G should be negative. So we know that an ice cube sitting on a lab bench at room temperature, or really above 0 Celsius, it'll melt spontaneously, okay? But we also know that if we take that ice cube and we put it in an environment colder than 0 degrees Celsius, it is not going to spontaneously melt. And that corresponds, that threshold is delta G equal to 0, all right? So how could we calculate that value? Well, if I play with this equation right here, and I've got delta H minus T delta S equals 0, and I'm going to rearrange this for, oh, bless me, for temperature. That was a perfectly timed sneeze. So let's rearrange this algebraically for temperature. And the way that I would do that is I could add this T delta S over to this side, right? And now I'm going to divide both sides by delta S, and I get a really important relationship, which is temperature equals delta H divided by delta S. And this temperature for this equation, that is specifically the temperature at which any process will become spontaneous, okay? So once again, at what temperature is melting of ice spontaneous at 1 atm? Well, we expect it to be 273 Kelvin, but let's double check, okay? And then it also looks like I made a mistake in my units here. So this should be 22.1 joule per mole per Kelvin. And now because we're dealing with ice melting, the thermodynamic quantities we want are fusion. So remember, that's the same as melt. So we want the delta H of fusion and the delta S of fusion. If we were calculating at what temperature does water spontaneously evaporate, then we would want the delta H of vaporization and the delta S of vaporization, okay? But all the same, we have the fusion quantities because that's what we want. So now let's just divide those and see what we get. So, and I'm going to, both of them are in joules per mole, so that's good. So 6.03 times 10 to the 3 is the same as 6030. So I just wanted to write that out in simplest terms. And that's joules per mole. And now, so entropy, recall the units are joules per mole per Kelvin. So I forgot that Kelvin right there. So now that's going to be 22.1 joule per mole per Kelvin. So let's do the numbers, okay? 6030 divided by 22.1. And look at that, I get 272.85. And I only have 3 significant digits here. So I would report that number as 273. And if I look at the units, my joule per mole and my joule per mole cancel. So I have 1 over Kelvin for my unit, which is the same as a Kelvin, okay? So that's pretty cool that this works out. Again, very simple math, but it's the concept that's important here, all right? My delta G equals 0 is special for the case at which a reaction or even a process will go from being spontaneous to non-spontaneous. And that's related to this relationship, okay? So we can summarize the following here. So again, I'm going to write this equation down. Delta G equals delta H minus T delta S. So for example, if we have a delta H that's negative, okay, negative, and we have a delta S that's positive, then this delta G will always be negative and thus always spontaneous. So we could think of this as if I have a reaction that's exothermic and leads to an increase in entropy, it's always going to happen spontaneously. And so if we back up and look at our combustion reaction for just a moment, right? So we know that these are exothermic because they're combustion, right? Combustion always releases heat. But how can I look at this reaction and guess if it's spontaneous? Well, look, I've got 2 molecules plus 25 molecules. So that's 27 molecules on this side. But then I've got 16 plus 18, which is 34 molecules. So right away, we could see that this reaction is going to get that test. This type of reaction will always be spontaneous, no matter what temperature it's at, okay? And that's true for all combustion reactions. So now, what if we have a negative delta H, but a negative delta S? Well, this is only going to be spontaneous at lower temperatures. And that lower temperature is given because now we know that this needs to be negative. But if delta S is negative, that's a negative times negative, which makes a positive. So in this scenario right here, I'll draw an arrow down there, we would want to see that the absolute value of delta H is greater than the absolute value of T times delta S. So that's why the temperature has to be small in order for this process to be spontaneous. Okay. So what if we have delta H positive and delta S positive? Okay. Well, if delta H is positive, that's working against us. But we can still have a spontaneous endothermic reaction. This time it has to be at higher temperature. So in other words, for it to be spontaneous now, what we recognize here is, once again, if I compare the delta H overall, we recognize that's a positive value, okay? Now this time I need this quantity to be smaller than the absolute value of T delta S, because there's a negative sign right there, and I need the negative to overwhelm the positive. And so that's why this is only spontaneous at higher temperatures. And of course, if I have an endothermic reaction, positive delta H, where entropy decreases, that is never going to be spontaneous, right? Because I have a positive, and then that's going to be a negative. Negative makes a positive. So again, if I have an endothermic reaction that decreases entropy, that will never be spontaneous. If I have an exothermic reaction that results in an increase in entropy, that will always be spontaneous. But now I can have exothermic or endothermic reactions that may or may not be spontaneous because I have to consider at what temperature it's occurring, okay? So be able to kind of rationalize things qualitatively using this type of a diagram, or this type of information rather, okay? So I'll see you in the next video.